Howdy, welcome to part 4 of chapter 5 for chemistry. And good news, this is the last part for chapter 5. We're finishing up the chapter by discussing what we call real gases. So all of chapter 5 was discussing gases in general, and we almost immediately introduced the concept of the ideal gas, because the ideal gas is, first of all, easier to analyze. Its behavior is very well predicted, and it's consistently applicable to a vast number of gases that we encounter in real life. But an ideal gas is an ideal gas. It's a theoretical construction, and the truth is that there is no gas that is an ideal gas. An ideal gas is strictly a theoretical construction. All gases are real gases. Most gases exhibit ideal gas behavior, but when we have a situation when a gas does not exhibit ideal gas behavior, we have to analyze it as what we call a real gas and capture the real physical features of that gas that are causing it to deviate from ideal gas behaviors. Okay, so let me go ahead and summarize what I just said. Most gases can be modeled in practice as approaching the behavior of an ideal gas. But in reality, there is no such thing as an ideal gas. Gases lose their ideal gas behavior when one of two things happen. Number one, they are elevated to very high pressures. Or, number two, are decreased to low temperatures. Okay, so you can sort of intuitively think about when a gas behaves ideally or not. And if you think about a situation, remember what the definition of an ideal gas is. It's one where the particles of that gas do not interact with each other. So if you're at very high pressures, the gases are being compressed, the particles of the gas are being compressed such that they're very close to each other. And it's impossible for them to be so close to each other and not interact with each other. And so they lose the ability to interact independently, and so they start to exhibit real gas behavior. They lose that ideal gas behavior. Likewise, when you're at low temperatures, the particles, their average kinetic energy decreases, and so the particles start to slow down, and there's more instances and more opportunity for a given particle to interact with another given particle. So at low temperatures, the gases have a tendency to lose their ideal gas behavior and need to be modeled as real gases. Okay, so we can say that in general, low pressure or high temperature gases are generally considered to behave as ideal gases. Okay, but for those cases that we don't have ideal gas behavior, the question becomes, how do we model a gas that does not behave as an ideal gas? And this is when we introduce the concept of real gas analysis. So when we have a gas that can't be modeled as an ideal gas, we have to use what is called ideal gas analysis. Okay, so there are two key ways that real gases differ from ideal gases. And by virtue of these two ways that they differ, we can develop the real gas analysis. Okay? So there are two key ways real gases differ from ideal gases. Number one, the particles of real gases are actually, the particles of real gases, not are, let me erase that. The particles of real gases actually occupy volume. Whereas the particles of an ideal gas are assumed to be volumeless. Okay? So again, if we had a system of particles for an ideal gas, and we had our container had a volume of 5 liters, we would say that the volume of the gas is 5 liters. It's occupying the whole 5 liters. But now, if we have a real gas situation, and this is in a container that is 5 liters, the volume of the gas is less than 5 liters because the particles themselves are taking up space. And so it's not possible that you can have the full 5 liters of this volume be occupied with the gas because there are other particles that are occupying the gas, okay, or that are occupying the volume. So that's number one. Number two, and this gets back to this idea of high pressure, low temperature, the particles of a real gas interact with each other. That is, if you think back to the very first lecture that we had on chapter 5, we introduced this idea of intermolecular energy mode. Okay? Whereas, if you remember, the particles of an ideal gas do not have that energy mode. Okay? So when we go to model a real gas, we have to account for the volume effect and we have to account for the energy effect. And we're going to account for the volume effect directly by subtracting off the volume that the particles of the gas occupy. And we're going to account for the energy effect by doing a pressure correction, okay? Remember that pressure is a form of energy, and so we're able to capture that, that energy effect by doing a pressure correction, okay? Okay, so to resolve the first issue, we will suppose that the volume occupied by the particles of the gas is given by N times B, where N is the number of particles and B is what we call an empirical constant for a given gas. Okay? And real quick, what does that word empirical mean? The word empirical means that it's experimentally, or what we call phenomenologically determined. Okay. Phenomenologically means that it's representative of a phenomena that we see. Okay, so experimentally or phenomenologically determined. So the opposite of an empirical constant would be a fundamental constant. That is something that is the same for every single substance, every single situation. It's a constant of nature, right? It is what it is. And we definitely have those constants. I don't think you've learned about any yet, but when we do, I'll be able to highlight the differences there. Okay, so this B value is what is called an empirical constant. Okay? All right, so if you remember, right, that an ideal gas is modeled as pressure times volume equals number of moles times gas constant times temperature. Oh, there we go, R. R is a fundamental constant, right? The universal gas constant as compared to an experimentally determined constant, okay? Okay, so we can rewrite this so that P is equal to nRT divided by V. Okay, just a simple algebraic manipulation. But then we can say that the pressure of the real gas and we're going to use the pressure of the real gas to be P prime is equal to number of moles times the gas constant times temperature divided by now the volume of the real gas, which is the volume of the tank that occupies the real gas, minus the volume of the particles composing that real gas, this N times B. Okay? All right, hold on to that thought, and we're going to come back to this in just a minute. We need to now resolve the second issue. So to resolve the second issue, and remember that the second issue is that real gases have intermolecular modes of energy we recognize that the particles attracting each other will lower the pressure In other words, they have this tendency, because they're attracting each other, they have this tendency to pull each other closer together, thereby compressing themselves and lowering the pressure, okay? Compressing themselves, thereby expanding the space that they occupy and lowering the pressure. So that is the observed pressure what we'll call POBS will be lower than if the gas behaved ideally. Okay? So think about this conceptually. If I were to say a good example are the gas cylinders up at the cabin that we fill with propane for the furnace, okay? So actually propane tends to behave as a real gas. We can more accurately model that as a real gas than as an ideal gas. And so there's a fixed volume that the cylinder has, and we'll take it to the store and we'll pump it up with natural gas until it gets to a certain weight. And the store doesn't measure the pressure, but if you were to measure the pressure after that filling operation, you would get a measured pressure. Well, that would be this observed pressure. Now, if propane exhibited ideal gas behavior, you would do that same thing, fill it with gas, weigh it and fill the cylinder with gas until you reach a certain weight, and then measure the pressure of that ideal gas, and that ideal gas pressure would be higher than this observed pressure. Okay? So that's what the observed pressure is the actual pressure. It's in reality the pressure of the real gas. But now we still want to model this. And so we go back to our ideal gas equation, and we then recognize that this observed pressure, POBS, is our P prime minus a correction factor. Remember that P prime was the pressure of the gas after undergoing the volume correction, okay? So we take that pressure of the real gas after undergoing the volume correction, and then we apply another correction factor for the pressure effect, which then is now the right-hand side here. So nRT divided by V minus NB, and that's P prime. And now we need to subtract off the correction factor. And so this is minus that correction factor. Okay? Okay, so we're going to sort this out here more in just a little bit. But first, what we need to know is that this correction factor depends on the number of particles in the gas and is generally given as, so this is our correction factor, and we write it as A, which is an empirical constant, times N divided by V squared. Okay? So we don't go into how this is developed, this A times N over V squared. We don't go into how that's derived, but it's all based on empirical or phenomenological observations. Okay? So there was a dude way back when who would do precise experiments with different types of gases in fixed volumes to known pressures, known weight, known temperatures, and take measurement after measurement after measurement of a bunch of different gases, and was able to observe that when he would go to do the correction for the pressure of that real gas, the correction factor generally followed this pattern of behavior, okay? And so he was able to fit this equation to the data that he had collected, okay? That's what we call an empirical correlation or a phenomenological correlation, okay? There may or may not be any fundamental behavior, any fundamental physical model that we have that allows us to back out this expression, okay? And so therefore it's determined phenomenologically, and we call it therefore a phenomenological or an empirical correlation, okay? Okay, so now what we can do is we can take this value for the correction factor and we can put it back into our observed pressure equation. And so we get that P observed, OBS, is equal to our P prime minus our correction factor. So minus A times N over V squared. And now this equals the right-hand side stuff. So nRT divided by V minus NB, and then minus our correction factor, which is A times N over V squared. Okay? Okay, so this is the pressure that we measure. Okay, so this is, say, our measured pressure of the real gas. This is the volume of the container. That the gas occupies. This is our volume correction. And then this is our pressure correction. Okay? Now, these constants, B and A, you have to get those from a table. And so you get values of A and B for different gases from table 5.3. Okay? Okay, so now we can, this is all very messy because of my notes, so we can just go ahead and rearrange this and make it nice and pretty. So we can rearrange this expression. Which then results in what we call the van der Waals equation. So do you remember how I said there was some dude way back when that took a lot of measurements? Well, that was Mr. van der Waals who did that. So for all his hard work, he gets an equation named after him. So we have POBS plus A times N over V squared. And this is all equal to V minus NB. And this is all equal to, oops, I'm so sorry. I wrote this wrong. So POBS plus A N over V squared times, not equals, times V minus NB. And this is all equal to nRT. Okay? And so then this portion of the van der Waals equation, so this whole thing is called the van der Waals equation. And so this portion here with the pressure is the corrected pressure. And it's the same thing as the ideal pressure, P ideal. And then this is the corrected volume. and that is equal to the ideal volume. In other words, notice that it's P times V equals nRT, which is the ideal gas equation. Okay, congratulations. We're done with Chapter 5. So do the problems associated with Chapter 5, and we'll work at setting up an assessment, and then you'll be able to start Chapter 6.